Okay, gang, you go to the zoo, huh? You go to the zoo and you see the peacock. And the peacock spreads its feathers. And as the peacock turns, you notice that the colors of those feathers kind of change a little bit. Or you see a child blowing bubbles, great big bubbles, and the bubbles floating off in the wind, yeah? And you look at the bubbles and you see, wow, what do you see? Beautiful rainbow colors in the bubbles. You see the spectrum. You see all the colors reflecting from the bubbles, isn't that right? Or sometimes you take like an abalone shell, and you hold up the abalone shell and you see the beautiful colors. We call these iridescent colors, yeah? And you're looking at the shell, and then you turn the shell a little bit, and hey, wow, the colors change a little bit. Or sometimes on a rainy day, you look at gasoline on a wet street, and you look at the gasoline splotches, and wow, man, they're beautiful colors. And they're rings of colors, too. Did you ever notice that? The rings go all the way around. Like if you got green, the green will continue and come all the way around. It's sort of like a contour map, a microscopic contour map of the different elevations of the gasoline on their wet surface. Whenever you have a double reflection like that, oftentimes I should say, when you have a double reflection from two surfaces, these double reflections give you beautiful colors. We call these interference colors. We talked a little bit about interference before, gang, remember? Let's briefly review that. Interference of waves. Consider a wave, like this maybe, yeah? Now consider another wave lopped right on top of it. Same frequency, same step. Physicists say same what? Phase, okay? Right in phase. Those two waves will add together to be what? A wave of greater amplitude. Greater amplitude, same frequency, okay? No big deal. But how about this? Consider a wave and another wave starting maybe here, you know, starting at a different point. That wave is out of phase. If it's half step out of phase, we say it's 180 degrees out of phase. These two waves are out of phase with one another, 180 degrees. They combine to produce what, gang? Ain't that nice? None. Right? They cancel out, okay? One wave cancels another. The same thing happens with light. I can show you what I mean with this laser. I'm going to shine a little laser spot on the wall. I'll put the lights out. You guys see that some places there it's there's little dark splotches. In some places it's very bright. Let's talk about that and see what's going on. What happened here now, gang, is the light's coming through a piece of glass, and the glass is irregular, and it's kind of fanning out, making a spot on the wall. But there's bound to be some places where that light comes right in phase here with maybe another from another point over here, but they come right in phase and be extra bright. And right down below, it might be light coming in like this, and light coming in from another little part of that little lens really there, like that. And where those two gang up, guess what they do, gang? Begin with CO. Cancel out. Cancel out. And over here, they add up. So over here, you'd have a region that's dark, okay? And that little dark region is the result of light interfering, okay? Destructively. Over here, it's light interfering constructively. So you get those bands or those little splotches because of that light interference. You get the same type thing with gasoline on a wet street. Here's some light reflecting off some water, okay? Light reflects off the water. And your eye is up here, and your eye sees the light. Let's suppose this is blue light, pure blue light, shining down, okay? Shining down on some water, and bounces off and gets into your eye. Let me ask you a question. What color would the eye see? It's an easy one. Begin with blue. Begin with B. Okay? You can see blue. You can see blue, right? But let's suppose it's not shining on water. Let's suppose it's shining on gasoline. Now what color is the eye going to see? Begin with B. Blue. It's still going to be blue because it's reflected, and we know that light doesn't change its frequency when it reflects. If you got a blue shirt on, you stand in front of a mirror, what color is the image? How about a red shirt? Could you do green? You get the idea. Okay. Light doesn't change frequency when it reflects. But what if this gasoline is floating on a surface of water? And it will do that. Now you've got two surfaces. Some of that light is reflecting off like this, but some of that light goes down through and reflects off the water surface. And if it does that in such a way that this distance puts the reflected wave 180 degrees out of phase, or out of phase 1/2 step, then when it gangs up with this one, what's it going to do, gang? What's the eye going to see? Nothing. The eye is not going to see light. The light's canceled out. Do you see that? Now, how thick this is has to do with the wavelength of light. What will work for one thickness won't work for another. And it has to do with whether or not the light changes phase when it hits the different surfaces. I'm not going to get into that part now. It's footnoted in your text. Suffice to say, light from a double reflection might have such a extra distance that by the time it gets back up here, it's out of phase with the part that reflected from the top. That is destructive interference. The eye going to see nothing. You're not going to see this in your local environment. What you will see in your local environment is white light from the sun. The sunlight coming down and hitting the gasoline on a rainy day. You've all noticed that. You notice that? It's got to be a rainy day that the gasoline gives you the color. Why? Because the gasoline got to float on water to give you two surfaces to make reflection from, yeah? Okay? Now when white light hits, for this particular thickness, the blue is gone. You check with your neighbor and see if your neighbor knows. If the blue is gone from the white reflecting, what color is the eye going to see? Go. What's it going to be, gang? How many say a yellow or an orange or something like that? I mean, yeah, the complementary color of that shade of blue, yeah? We talked about this. We talked about the blue sky, remember? The blue sky scatters off blue. So given enough sky for the light to get through, by the time that light gets to you and all the blue is scattered, what do you get left, gang? You get the complementary color, okay, sort of like the orange or the yellow, yeah? So when you take one color out of white light, what you see is the complement, huh? In the same way the water absorbs the red, and so what do we see the red? What do we see the water? We see the water as cyan, the complementary color. Same type thing here. Now if you understand that, you can see this. Let's suppose the light is coming down, the same thickness of gasoline now, but the light is coming down at a more grazing angle and bounces to your eye. You could do that by taking your eye and you say, hey, I see it's sort of a yellow, and you go down like this, and all of a sudden, ooh, it changes to a different color. And someone says, how come it changes? And you say, what is? No reason for that. Different angles, different colors. Maybe that's no. Come on. Why does it change, gang? The apparent thickness would be greater, wouldn't it? If you're coming in at an angle like this, isn't that a thicker path than this one here? Huh? It's like a worm crawling through a book. The worm crawls from the book from here to here. It says, hey, pretty short book. Now you hold the book like this and the worm crawls through. It says, my gosh, an encyclopedia, okay? You'd get a different apparent thickness for the way you hold it, yeah? And the same thing would happen with light. And so light coming in like this, boom, boom, boom. You would cancel a longer wave or a shorter wave. Neighbor. Through a longer path, would you cancel a longer one or a shorter one? Longer one. So let me ask you a question, gang. Let's suppose you happen to cancel out the yellow. And where you're seeing, honey, you ain't seeing the white light. You're seeing the white and the yellow ain't there anymore. The yellow been canceled. What color your eye see? E. Check it. What's the neighbor say? If you cancel the yellow, the eye you're going to see what? Blue. Can you see it's blue? Get it? This Saturday night when you take your bath, use some soap. In fact, splurge. Use bubble bath. Get a whole lot of bubbles in your bathtub. Now you're taking your bath, you light up above, it's an incandescent lamp, white light. Okay? White light shining down to the bubbles. Take a look at those bubbles closely. Guess what, gang? The highlights ain't white. The highlights are all different. How many people have noticed that already? How many people have taken baths year after year after year and never looked at the bubbles? Look at the bubbles on Saturday night and see if you don't be seeing the bubbles got different colors. And your friends say, how come the different colors? And you say, that's an example of Begin with I. Interference. Interference. That's right. You got a bubble like this. Maybe you got the white light up above, okay? Okay. And the white light coming down. Here's your eye right here. Okay. Light come down, hit the bubble, bounce to your eye, huh? But some of that light bounces from the bottom surface and goes to your eye. Isn't that right? Aren't there two surfaces to that thin bubble? Isn't that right? That thin film. Two surfaces. Part bounces from the top surface, part from the bottom. Hey, what if that extra distance going down through is such that it will cancel out one of the frequencies over here? Then, honey, that eye ain't going to get it. Now, if you got white coming down and there's no cancellation, boom, you're going to see white. But if one color is canceled, you're not going to see white. Let's suppose the color that's canceled happens to be red. Then the eye will see what color for that particular bubble. Do you guys know your color rules? You got to know what the complementary color of red is. We take all the red away, what do you got? You get that green cyan. You get that cyan, the greenish blue. So the eye over here is going to see what? Greenish blue. All right? Now you point to the bubble, you say, hey, that's a greenish blue bubble right there. Your friend. Your friend looks down, and your friend looks at the same bubble. But for your friend, this is a different thickness being canceled. Maybe this different thickness, maybe what's being canceled here is the yellow. And so your friend sees that light, white minus the yellow. You say, hey, look at the greenish blue bubble. And your friend says, no, it ain't. It's a blue bubble. So your friend says it's blue. You say it's cyan. Who's right? Me. What happens in the tub? I say it's cyan. I say it's blue. I say it's well, boom, bubble bath. Okay, you see what's happening? What color you see depends upon what? With everything. What you see depends upon what? Do we all see the same thing? Huh? Depends on your point of view. Open up the hood of a car. Have a mechanic look at it. Now you look at it. You see the same thing? You see the same thing? I remember years ago, a guy was passing around a picture of his girlfriend. He said, hey, you want to see my girlfriend, man? Look at this. He takes out this picture. He shows the picture. And we're all looking at it. We're feeling sorry for him, you know? But to him, that's my girl. And we're like, oh, my God. And you start to wonder, do we really all see the same thing? Huh? Well, over here at least, the different bubbles depend upon your point of view. Where your head's at, right? What you see depends upon where your head's at. Yeah, okay. You get the different colors. You know these camera lenses? You see these camera lenses? You see that violet hue on the camera lens? Ever see that? Coated lenses? And they look violet, don't they? Do you know why they look violet? No reason for that. It's just one of those things. Now, come on. Do you know why they look violet? There's a color being canceled. There's a color being deliberately canceled. And the color being deliberately canceled is a color that we're most sensitive to. And if we want to cut down back reflection in that lens so we don't fog up our film, and we can only do it for one color, we're going to pick the color that the eye is most sensitive to, that the sun is emitting mostly off. And what is that color, gang? Begin with a Y, end with mellow. Try it. All right, then Y-E-L-L-O-W. Try it. Good, good. Okay, we got it. Okay. Here's what happens. You have these lenses. Camera. Here's what a problem is. Light will be coming in and come to focus right there, and that's nice, because you got your camera film right there, and you want to come to focus. But some of the light reflects off and comes out, you don't care, but then comes back in, reflects off, you don't care, and then comes over here. And part does this. And that comes to focus here. And so what it's going to do is fog up your film. You don't want that light getting there. You like to get rid of it. There's a way to get rid of light. You can cancel it. So what you do, at least for the yellow part, you can put a thin film there. And that film is 1/4 the wavelength of yellow light. So the light that bounds from here also is ganged up by light that goes here, a quarter, a half. And what happens is you'll cancel it out. And so that thin film will cancel all this. It won't happen, and you'll be back to your nice, sharp picture. At least for the part of the light in the middle of the spectrum. So you, out here, look at the little thing. If it's canceling yellow on this side, it's canceling yellow on this side. because the same type thing. You're getting a double bounce out here. So when you look at that purplish surface, that purplish surface to lenses, it isn't like they get some purple gunk they put on there. No, 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 no. It's very, very clear. But the thickness is such that it'll cancel out the yellow and give you the complementary color, so you see your coated lenses that nice purplish color. Ain't that neat? You like? Yeah. I thought that's kind of neat. Gang, we're going to talk about polarization. We talked about charge polarization before. We talked about like negative being on one side of a molecule, positive on another. Polarization in this sense is altogether different. We're talking about the lineup of waves. If I take a rope and tie it to the wall, and I shake the rope up and down like this, guess which way the wave will vibrate? How many say, oh, probably like this? Come on, trick question. No, no. If I shake it up and down like that, the rope will vibrate like that. And the vibration is aligned. We don't say aligned, we say it's polarized. If I shake the rope back and forth horizontally, then I'll generate a horizontally polarized wave. Okay? You saw the example in the textbook. If I pass these waves through a picket fence, maybe the picket fence can filter them out. It turns out if I have a picket fence where the fence staves are all vertical, and I have vertical openings, and I shake my rope and it goes right through the opening, it's like the opening weren't there. The shake goes right on through, and the wave travels. And that's easy to see. This is very conceptual. If I take the rope and shake it sideways, however, whoom, the vibration can't get through the fence. And so what the fence does is blocks it. And so that's a filter. And I have over here such a thing. Here's a polarization filter. Okay? And that's what this is. This will allow light to vibrate through going only one way, not another way. I don't know what the plane of this is. I can't see. But let's suppose it's like this. I have microscopic picket fences like that. I have in the back here a piece of white material that will diffuse light so that when I shine light through it, there won't be too much glare. But nevertheless, this is a piece of Polaroid filter. And let me tell you how this came to be. It turns out that non-cubic shaped crystals, all non-cubic crystals, say something like this, or like a diamond shape. All non-transparent crystals will pass light in two directions, the two preferred directions. The crystalline structure is sort of like an orange grove. You ever drive by an orange grove, you see all these trees, you see right down? And you're driving again, right down the cleaves, okay? There's certain preferred paths. Well, it turns out light will go through vibrating like this, and light will go through vibrating like that. And over here, no, you'd only get components here and components here. And it turns out in most crystals, the vibrations in one direction go through quicker than the vibrations in the other. So it's a little time delay. And you get beautiful colors as a result of that. Get into that a little bit later. But for now, there are some crystals that take this one here and cut it right down, and it's absorbed. This was known at the first part of the century. A lot of people knew that there were needle-shaped crystals that would pass light in only one direction only. A fellow by the name of Edwin Land knew about that and did something about that. What Edwin Land did was took all these crystals, this crystalline material, made it into sort of like a jelly, put it on some cellophane, and stretched it. And when he stretched the cellophane, guess what these things here did? What would happen if you had a whole bunch of needles on a piece of plastic, and they're pointing every which way? And you take and you stretch the plastic out. What will the needles do, gang? Won't they kind of all line up? That's what Land did, and they got them all to line up. Then what he did is he put it down, he put another piece of plastic on top, took his wife's iron, and ironed it, and cemented those needles together, and made more than $1 million. Edwin Land patented it, and these are Polaroid filters, and that's what they, in a sense, are. Is they're made up of molecules in here, which are crystals or molecules, that are all lined up in one direction and will allow the light to pass through one way. I can kind of show you that with a lamp here and using two of them. You can still see the light. These things must be lined up. What's coming through one comes through the other. But let me turn it. What happens right in there, gang? Right in there. Can you see if the light doesn't come through? Or I could hold this like this and just turn this. Comes through, comes through, comes through. Doesn't come through, not so much, not much, and there it's blocked off. Ain't that nice? Now, HC. How come? This is easy to see. It requires a knowledge of vectors. The arrows. Let's take a look. Let's suppose my lamp, my original Polaroid, is like that. Light coming through. What kind of light going to come through, gang? Light hitting it is like this. Like this. That hits it. Boom. But the only part that comes through is the part vibrating like this. So what comes through is light vibrating like that. When I put the other Polaroid in the way, the square piece, what happens if, well, let's try this first of all. What happens if this and this are lined up? Will these vibrations get through there? It's a vector falling right through there, and whip, boom, out it comes. So the light's not cut out. What happens when I rotate it 90 degrees? Okay. Is there any component of this along that direction? Remember we talked about the bowling ball before in the alley? Being pulled straight down, a vector straight down, and we said, is there any component 90 degrees to it? And the answer began with an N. No, same type thing, see? We got a vector, vertical, there's no component there, so nothing gets through. That's what you saw. What's kind of interesting is at an angle. Let's suppose I put this at an angle. Now this falls on top of there. As you recall, did any light get through? Yeah, some got through. And here's where your vectors come in. This vector here has a component along this direction and a component along this direction. Guess which component won't get through? This one or this one? This one. That won't get through. See? And you guys remember this? You take a little component here, huh? And here's a other component here. And here behaves as if it's really this one and this one at the same time. This one doesn't make it, but this one does. And look what, some comes through. This one is not as big as this one. Did you notice the light was not as bright? So the light is dimmer, but nevertheless, some comes through. And rock this all the way around, this component keeps getting smaller and smaller and smaller, and finally shrinks to zero, and whip, boom, nothing gets through. So that's what happens with these Polaroids. Kind of neat, huh? It turns out that when light reflects from surfaces at a grazing angle, the polarized component is preferred. You know, if you're like driving and you have a road surface and the light is coming down hitting, it turns out the light that will make up the glare is polarized in the same plane as the surface. Do you ever take these scaly rocks and go out in a pond and you get flat rocks and you want to scale them across the surface? If you take the rock and you throw it kind of flat, sort of like this, okay? Boom, it'll ba-boom, bounce off, yeah? How about you throw it like this? Kind of go down, yeah? Light does the same thing. Light that's coming down like this, bounce, huh? Light that's coming like this gets absorbed. So that's why you get the glasses. What kind of Polaroid glasses would you wear to cut out glare from horizontal surfaces? Let me show you 3 pair. Which would you use, gang? These are these for driving. You got a truck driver and you're going to drive along the road. Which pair of Polaroids? How many say they're all the same? How many say I'd wear these ones here? Squint City, honey. What's going to come through those glasses? Polaroid light. You have to drive like this, okay? You're going to go a cup of coffee, please, okay? Occupational, you know. Okay. No, these are what you get. See, the Polaroid glasses that you buy are usually like this, because most of the glare comes from horizontal surfaces. What if you're a painter all the time and you're painting vertical surfaces? Then you probably wear glasses like this. I don't know where you'd get them, okay? But usually the glare is horizontal, so we cut the horizontal off like that. You got like that, honey. That light come in, boom, it's okay, blocked. And now what you see is without glare. Do you know what these pair are for? 3D movies used to be popular. Used to be 3D movies where you have two projectors going at one time, and you've got to see each scene independently. So they polarize one this way. You got glasses that way. The other projector's polarizing this way. You got glasses that way. Boom. Each eye sees an independent view and 3D vision right there. Questions on that? Question?
Yeah. A Polaroid glass doesn't necessarily cut out UV though, right?
No. The function of Polaroid glasses is to cut out the horizontal component of all light. It turns out all glasses will cut out UV. All glasses. Now, what part of the UV? Very, very close to the visible part, a lot of glasses will transmit. But the high frequency UV, the kind that's dangerous, all glass, and I believe most plastics will cut it out. So anyone that's wearing glasses, you don't have to worry about UV light hitting your glass. Any kind of glass.
Have you heard of the blue blockers?
The blue blockers. I haven't heard of the blue blockers. A new kind of glass?
Yeah, supposedly it cuts back on the blue rays.
Do you pay more for it?
I don't know.
Yeah.
I don't have one.
Yellow lenses.
I mean, there's a lot of things that these glasses will cut out the UV. Well, honey, what glasses won't? You know what I'm saying? So. I got a question for you, gang. Something nice. Keep you entertained a little bit. See this? Okay. I remember the first time I saw what I'm going to show you now. A fellow came in my office when I was a graduate student, and he had 3 sheets of Polaroid. I've never dealt with 3 sheets. 2's enough, yeah? And he had 3 sheets, and he says, "Hey, Hewitt, if I take this 3rd sheet and I put it in front, will light come through?" I said, "NWH," right? Okay. He said, "How about if I put it in the back? Will now light come through?" And I said, "NWH," right? He says, "How about if I put it like in between the 2? Will light come through then?" I said, "NWH." He's, "Oh yeah?" There's your light, honey. What's this NWH? Can you kind of see that? Light is getting through. That's sandwiched in between. Over here, no? No? Yes. To understand that and explain that, you need to know something about vectors. You guys be knowing about vectors? Could you kind of make a little vector diagram showing how light does get through? I think you can all do it, particularly if you pay attention to your textbook. All right? And can you do that and hand that in next Monday? All right? Okay, great. All right, physics. Catch you later.